So please take your seats. There will be more time, I promise you, for networking. I know there's a lot of interaction going on and exciting, but that is the part of the objective of this workshop. So it's my great pleasure. Let's get it started. It's my great pleasure to introduce a great partner and a friend and visionary leader. I have been working with Dr. Siavash Isajade for more than 2.5 years now. Dr. Isajade is Senior Technical Director in the Technical Strategy and Innovation at Veolia North America. And I would request Siavash to introduce the panelists.
Thank you.
Okay.
Afternoon, everyone. Can you hear me? Now it's on.
Dan, what about those mics?
Can you hear me now? I think it's on now. Flip it the other way. Can you hear me now?
Okay, this one.
It's okay, I can use it. All right, good afternoon, everyone. Welcome back. And I hope that you enjoyed your lunch and networking time. My name is Siavash, and I'm very pleased to moderate this session at the Translation Research in PFAS Contamination from Industrial Perspective. Throughout this morning, you had a chance to hear from the regulator, from university academic innovation, and from the community. Now, this panel will focus on a question that how do we translate these advances into the real world solution for utility and community? We have a distinguished group of speakers representing research foundation, consulting firm, technology provider with a broad spectrum covering full spectrum of innovation to the implementation. We have Dr. Lauren Weinrich, Director of Research and Development in American Water. Then we have Dr. Charles Schaefer, the Director of Research and Testing Lab of CDM Smith. Then we have Dr. Jason Hnatko. He's an engineering manager at the Allonnia. And then we have Brent Alspach from Arcadis, Vice President of Research and Director of Technical Research. Each of our presenter would present their slide, and then we will follow up with a question and engagement with the audience. So with that, I would like to introduce our first speaker, which is online, Dr. Kenan Ozekin. Kenan is a research officer from the Water Research Foundation. In the interest of time, I'm going to be not introducing them in full. Please feel free to use the booklet that you have for their bio. And with that, I would invite Kenan to present his slides. Thank you, Kenan. Can you hear us?
It looks like he's frozen.
Hi, Siavash, can you hear me?
Yes, we can hear you.
Okay. And will you run my slides as well, or would you like me to share my screen?
You can share, Kenan.
Okay, because I don't know what the audience is seeing, so I'm just gonna go with
The feedback.
Okay, are we good?
Not yet.
Can you see my screen, Siavash?
No, Kenan, we cannot.
You cannot. Okay.
Could you try one more time?
Yeah, I'll try one more time. Give me a second here. Share it again. How about now?
I believe we're sharing for you.
If
Kenan, we can hear you. We
okay,
can see
yeah,
you.
then I'll go without the slides. Siavash, it's okay. I'll just go without the slides.
Kenan, we can see it. If you want to go through that, we can see it.
Okay. Okay, from my end, looks like I'm sharing my screen. If you cannot see it, that's okay. We'll go without the slides.
We are seeing page 2 in your screen now. We do see it. It's page 2.
Yeah, we are seeing
Yes.
slide.
Okay.
Yeah. Okay. Yeah.
Perfect. Okay.
If you
Okay.
can go to the presentation mode, that would be good.
Okay, I will go to the presentation mode.
Perfect.
Okay, great. Thank you. I appreciate for helping with the technology and thank you for the opportunity to be here. This is a really important conversation for water sector, and I'm so sorry that I couldn't be there in person. I couldn't. I see most of my friends sitting around the table. I'm sorry that I'm not there with you, but I want to say hi to all of you. So today, what I want to do, I want to give a quick overview of our PFAS research at the foundation, where we have been investing, what we are learning, and what are some of the gaps that we are seeing in this world. So if I go to the next slide, so we began researching PFAS for a while, almost like more than 10 years ago. Over the years, we invested over $12 million for our PFAS research. I believe this is probably the largest amount of investment we did for a given contaminant. And over the 10 plus years, we funded over more than 35 projects. Now it's 39. It's actually now even 40 because we just funded a new project. And our research portfolio evolved over the years. When we first learned about PFAS, our first research was mostly trying to understand what is PFAS. Can we really use conventional treatment, for example, to remove it? So once we learned a little bit about PFAS more than 10 years ago, really then we began focusing on the needs of our industry, our subscribers. So our first research projects were mostly focused on the treatment and then also occurrence of PFAS. As we learned more and more about the PFAS contamination, our research investment also shifted to other areas. As you can see on this pie chart, our largest investment on PFAS has been on treatment, occurrence, but you are seeing destruction, residual management, and monitoring and communication as other areas that we've been researching. And as we again learn more and more about PFAS, the balance of this pie chart is going to shift. Right now, for example, there is more focus on the destruction technologies. So maybe in a few years, we'll see even a bigger pie of that will go to the destruction technologies. So the next two slides that I'm going to show to you are the list of the projects that we funded. I'm not going to go through all of these projects. However, I did want to give you a sense of type of projects that we fund at the foundation. So basically, we are looking for everything related to PFAS, anything from treatment to machine learning for source tracking, destruction pathways. And the other thing, important thing for us on the PFAS world is that we have a one water approach. So when we look at PFAS, we are not only looking at drinking water, we are also looking at wastewater, we are also looking at biosolids and impacts of PFAS in those in the biosolids as well. And one final point before even I come to this slide is that we've been collaborating with many different utilities as well as research organizations and also federal government to fund some of our projects. So next a few minutes, I want to talk one of our projects that we found that this is about innovation and disruption as well. So as we know, granular activated carbon is one of the proven technologies that is out there to remove PFAS. At the foundation, we have done quite a bit of research to understand under what conditions GAC can be optimized to remove PFAS. One thing about granular activated carbon after PFAS removal, it needs to be either reactivated or disposed. So it's a common method of the reactivation is through the thermal reactivation, and there are some facilities that do that. When we look at where those facilities are located, there are 15 of them that are all over the country, as shown in this triangle dots that are on this map. And you can see that they are in different places, and depending on where you are in the country, where you may have to ship your GAC hundreds or thousands of miles depending on your location. For example, if I am in Colorado, which I'm calling from Denver, Colorado right now, I want to get my GAC reactivated. I need to ship it to a closest one will be in Arizona. That is hundreds to thousands of miles away from us. So that really creates a challenge for utilities in terms of how practical it is to ship GACs far away for reactivation. The second is, of course, the impact of that shipment, extra costs associated with it. You can even talk about greenhouse gas emissions associated with that shipment. So one of the projects that we funded is actually looking at this in a different way, trying to see if we can actually regenerate GAC at a utility setting. And so the project that we looked at is microwave regeneration. It was funded back in 2020 by Clemson University researchers. And they did look at the bench scale about impacts of microwave technology to reactivate GAC. And they found that it can work. It was very successful. They were able to remove 90 to 100% PFAS. And then they also were able to see that the reactivation did not impact GAC characteristics. So follow up to that project, then we took those results and funded another project with the same research team, and that now they are testing everything in the pilot scale. So you can see the innovation from bench scale to pilot scale. And then eventually, once we are done this project, the next step is taking this technology to full scale because we are seeing very, very promising results. If this is very successful, utilities will be able to buy their own reactivation microwave. They can use it at their facility without making a shipment. They can reactivate it at their own schedules. So this is really, really, really good news for our utilities, and it can show the innovation on this space. Other topics that we are looking at, residuals and biosolids, and this is where I'm going to end my comments, is really the next thing about PFAS right now is all biosolids. There's quite a bit of focus on understanding PFAS concentrations in biosolids, stability of PFAS, as well as distracting PFAS in biosolids. So if I want to summarize everything that I said, PFAS is very challenging, complex problem for all of us. Through our research, we've been providing tools and solutions to help utilities address this complex issue.
And thank you for your presentation. Please stay patient with us until the Q&A session. Thank you.
Sure.
With that, I would like to invite Dr. Lauren Weinrich from the American Water.
All right. Hopefully, I will have some slides here. Well, it's always great to go after the Water Research Foundation. We've done a lot of work with the Water Research Foundation. I think that one sliver of the pie for the communications, that was a project that we did at American Water early on, planning the gap to fill in communications between water utilities and our customers. So appreciate the foundation's support of that. Okay, here we go. Thank you. So while this is the title slide, I'll move to the next slide. So I just wanted to give an overview of American Water. If you're not familiar, but many of you, if you're in New Jersey, may be a New Jersey American Water customer. So I am part of American Water, and I'm the director of R&D for the company. So our footprint extends over 14 states and additional sites where our military services group is. So I just wanted to highlight that on here in terms of, you know, the types of water treatment plants that we have, the extensive research that we've been doing on PFAS. I'm excited to share and talk about that with our panelists today. We have 80 surface water treatment plants, a number of groundwater treatment plants, and given our footprint, we've been treating PFAS in California and New Jersey for some time now. So part of the benefit of working in the R&D group is we get to take those lessons learned from certain states where maybe the regulations have advanced a bit more quickly or have different issues, and bring that knowledge base to our footprint as a whole. I want to mention the bottom line there, that over the next 10 years, we plan to invest $46 to $48 billion in our systems. So that investment is inclusive of a lot of the PFAS treatment that we need to put in place. There were a few numbers thrown out today in the millions and billions. And yes, across our footprint, up to $48 billion is what we're projecting in the next 10 years. So that was the company. I want to talk about my team a little bit. So this is our research and development team at American Water. I'm very proud to highlight that this is our 45th year, our anniversary / celebration of having a research department at American Water. It's unique for utilities often to have a research department, so celebrating this legacy where the topics have spanned many things, and obviously PFAS has taken over for the past decade or so. But established in 1981, we've been a cornerstone of American Water, and this is the team below. We are based here in New Jersey, down in Delran at one of our treatment plants, as well as out in Illinois at our central laboratory and compliance laboratory. So just want to highlight that. And as I mentioned, the research that we've done at American Water really runs the gamut. Obviously, PFAS, I put, first and foremost there on the top left. But we have to keep in mind, from the utility perspective, PFAS is not the only thing that we're concerned about. PFAS is not the only area of research that we need to invest in or find funding for or have resources to look at and understand. Between DBPs and the upcoming MDBP or Stage 3 rule, ongoing challenges around opportunistic pathogens and understanding more about them. It's April and HAB season has already kicked off. So it's just one of those, really important points that we are looking at and arm in arm, shoulder to shoulder with our other utility partners and at other utilities where these focus areas continue to grow. We need to come together, share expertise like coming together today to find the solutions to these challenges and drive that expertise and collaboration. So just wanted to highlight a little bit of the collaborative thought leadership that we have through the R&D department. First and foremost, there is the piloting that we've done. Currently, we have over a dozen pilots going on at surface water and groundwater plants across our footprint. This is testing a number of different types of media. We do test novel medias along the way, in addition to the best available technologies. But in the past, we focused on short chain PFAS. We developed methods along with the EPA at the time and published that as part of one of the Water Research Foundation projects, 4913. We're presenting that. We're bringing this information out. See a lot of our collaborators here in the audience and making sure that we are talking about the challenges that utilities have and the solutions that we're finding as well. Part of it also is to work with others that may not be in the utility space. So from advocacy and also understanding what other entities like the U.S. Chamber of Commerce is looking at, where they've stood up their own focus on destruction technologies and focus area of that. So overall, this is an important piece to underscore the collaboration that's needed. It's not just the leadership, but it's coming together as utilities and with our partners in academia and consulting to find solutions to these challenges. Kind of underscore the treatment costs. The numbers are there. What I also want to highlight on the left is that it is a puzzle piece of all of these points that go in. It's not just the cost for the media change out or installation of the units and systems themselves, but it's the testing, the monitoring. When do we change that out? How much of a laboratory capacity do you have? Do those samples need to be shipped out? And also communicating with the public, conducting other testing, the operation and maintenance costs in addition to the capital costs are exorbitant. So as we do these pilots and partner with our innovative technologists, we want to bring, as a utility, that real world perspective of those different water types, qualities that impact treatment that may work in one place. As DEP was saying, every solution is not a one size fits all. So as utilities, we are here to partner with you and understand where those challenges come up and try and figure out a way to address them. So my information is there. Happy to connect with anyone after this, and I'll turn it back to you, Siavash.
Thank you, Dr. Weinrich. I was a first-hand witness of observing Dr. Weinrich and her team excellent work on detection of PFAS a long time ago. Now with that, I would like to invite Dr. Charles Schaefer. He's also the one that I follow his work and research very closely, and I would hope that you would enjoy his talk too. Charles?
Thank you very much, and it's a big honor to be able just to share a few thoughts this afternoon with everyone here. So what I want to just talk about are maybe a few considerations when trying to implement or develop a new technology, some things to think about that might be important for both determining when the technology might be important and also its effectiveness. And one of the big issues, and this was brought up in some of the earlier panels, is really understanding the PFAS that are there, which can be real important for selecting a technology, but also for evaluating and looking at a fluorine mass balance. On the left is some data that working with Bridger Royal and others is actually in part, it's part of a Water Research Foundation project, looked at the PFAS composition in a domestic wastewater treatment plant, looking at the influent and the effluent. And really in those pie slices there, what's in red, those are the analytes that you would get from a typical commercial analysis. And you could see 11 to 20%. The kind of peach colored is what you would get with the top assay, and that's applying an aggressive oxidation to turn all those precursor compounds, or that black box of compounds, into things you can detect. Well, that's pretty significant. That accounts for about half of maybe the traditional PFAS mass. But look at all that blue there. Those blue are your polyfluorinated and monofluorinated pharmaceutical compounds. And that's really a big fraction of what's there. So if you're trying to do like a total fluorine balance or total organic fluorine analysis, most of what you're going to be detecting are really not your traditional PFAS, at least in wastewater, but it's a lot of these fluorinated pharmaceuticals. Again, this could be real important if you're trying to evaluate a technology or close a fluorine mass balance. But it's not just wastewater. Think about drinking water. It's the study, the data on the right is a figure from a study that was performed a few years ago. And what they looked at is an expanded PFAS analyte list. They had some standards, so they looked at some things which really aren't currently commercially available. And the dark blue is basically your sum of PFAS if you use a 537 or your 533 analyte list. And you can see for some samples that that was maybe a significant fraction, but the light blue is just adding additional analytes and using some additional standards to quantify that. And you can see in many cases, even in drinking water, a standard PFAS analysis is really not capturing everything that can be quantified there. So again, these are important considerations when choosing and maybe more importantly, evaluating a technology. So another consideration is, especially when you're considering types of destructive technologies, is what sort of matrix should you be thinking about? And I think in many cases, thinking about treating a more of a concentrated matrix, it might really be the more feasible or economic target. So we've been doing some work as part of a few Water Research Foundation projects, looking at some of these concentrated waste streams in wastewater treatment plants, looking at some of the solids dewatering streams, those concentrates, where we see some much higher PFAS concentrations, looking at foams and froths and aerosols and things like that. Part of the work we're doing, you can see this is still in very early stages. You can see the very small scale there. But looking how PFAS accumulates, even in some of those very transient foams that appear within aeration basins. And what we're finding, I see the legends on my figure didn't come through. But basically what we see in there for PFOS is about a 90-fold enhancement factor. PFAS, especially long chain compounds, are getting very enriched there. And I think it's some of these concentrated streams, especially when you can leverage some of the processes that are already going on, whether it's in a wastewater treatment plant, maybe it's in some fixed bed sorbents, maybe it's in things like foam fractionate or things like that. Those can be really good targets for treatment. And as technologies are being developed, and maybe if you want the best path to success, think about some of these concentrated waste streams and where that technology can be applied. I think too many times destruction technologies and separation technologies are developed separately. And I think that's not always a good thing. I think trying to link them up earlier rather than later is better. And just one more slide here, and I stole this from my colleague Jeff McDonough at CDM Smith. This is just an illustration of a PFAS technology stream. It's not all inclusive. I'm sure there's some things missing there, and really looking at water. But you can see you have destruction technologies in red, some separation technologies in blue, and absorption like fixed bed sorbents in purple there. And certainly I'm not going to go through all of these. But the point is that there are a lot of technologies out there already being commercialized, right? And as a consultant who tries to evaluate or recommend technologies, it's challenging to stay on top of this. But as someone also who's trying to develop technologies and get them in the market, I think it's important to realize that a lot of the end users, a lot of the people who might be purchasing or using these technologies, man, there's a lot coming at them. It can be very overwhelming. And just understanding how a new technology fits in there, how it relates, competes, compares with these other things are very important. So I just wanted to paint that picture as well. So that's all I have. Thank you very much for your time.
Thank you so much, Charles. That was very interesting. Now that you have put that three over there. I would like to invite Jason to show us one of those technology that is in implementation. Jason, floor is yours.
All right, thank you. Thank you, Charles. It was a great job setting the stage for what I'm about to talk about. So I'm from Allonnia. So we're a technology provider for a technology called Surface Active Foam Fractionation to remove PFAS from water. We talk a lot about drinking water at this meeting, but I wanted to talk about some of the other challenges that we have with different types of water streams, particularly wastewaters. As Charles showed, you can actually have much higher concentrations of PFAS in a lot of those wastewaters, especially things like landfill leachate, AFFF rinse water, fire training water, remediation groundwater, industrial process water. We're talking orders of magnitude higher PFAS concentrations than the MCLs and what you'll find in typical drinking water. In addition, you also often have a lot of co-contaminants that you would need to treat to use something like carbon or ion exchange resin. We heard a little bit about those challenges with IX resin and some of the dissolved constituents in the drinking water. But you could have volatile organics, metals, other organics that are going to interfere with those sorption technologies. And then when it comes to wastewater, for drinking water, we have these MCLs that are published, whether they're state or federal, very clear standards for treatment. With other waste streams, we don't always have that clear guidance. So states will regulate to the MCLs, which may or may not make sense for certain streams. But you end up with this patchwork of different regulations, whether it's from states, local POTWs, and different guidance. So it makes it very hard to treat different water streams. At Allonnia, we use foam fractionation. So that separates PFAS from water using rising air bubbles to accumulate the PFAS into the foam or the top of the water column. Just like Charles showed in a natural aeration basin, it's a natural process. So we take advantage of that natural process to harvest a foam and remove PFAS. Right now, Allonnia has 3 different systems on offer, SAF 10, 20, and 40. And you can see here some of the different flow rates. We're talking about at the small scale, 14 gallons per minute, and at the large scale, 100 gallons per minute. And these are commercially available treatment units. We've already gone from theory to practice. You can buy these. There's permanent installations that are running these. But you sort of see a disconnect here between what I'm talking about and what Lauren talked about. We're at 100 gallons per minute in our largest system. And that's really not going to cover your smallest possible system. For drinking water utilities, we're talking about millions of gallons per day. For wastewater treatment plants, millions to hundreds of millions of gallons per day. So really there's a disconnect between the innovative technologies we have for treating PFAS and the need for the future. So what are those challenges and why is it hard to adopt and scale up these technologies? One of the first things is investment. So for most innovative technologies are developed at universities, they're brought into startups, they spin them out to companies. And I mean, Allonnia has been very successful in getting a technology from the bench to the field to commercial application with millions of dollars of investment. But to take the next scale, we need someone who's willing to put in tens of millions to hundreds of millions of dollars to build a larger scale system. And that's a big risk. It's a big risk for a utility or an investor or a company. So that is a kind of a hurdle to get to the next step, is getting that funding. Another difficulty we're seeing with adoption of the technology is regulatory uncertainty. People don't want to do anything until they have to. So will these current technologies meet future regulations? Are we going to keep extending deadlines for compliance? Are the limits going to change? Is the technology I get now going to work for the future? Which makes it very difficult. And then the last thing is risk aversion by end users, right? So at the end of the day, you get rewarded for solving the problem and getting rid of the PFAS. You don't get rewarded for being innovative necessarily. So taking a chance on trying a new technology gives you a lot of risk of exposure, of things going wrong, and it really doesn't have a lot of upside or benefit. So we need to find ways to incentivize that risk taking and getting people to try new things. So that's what I had. I do have a showcase with business cards. If people are interested in getting in touch later, come by and talk to me. Thank you.
Thank you, Jason. That was a great example of taking innovation and moving forward to deployment. Now, let's now take a look at the technologies are being scaled and implemented across the industry. With that, I would like to invite our friend Brent Alspach for this. Thank you, Brent.
Thanks, Yavish. Okay, I got some slides, I believe, here queued up. As I'm getting started, I guess on the lines of slides, And I appreciate, Siavash, the opportunity to talk to this group again. And you give us, what, 5 minutes, I think, to each. And last night I gave him 30 slides, which of course he commented on, and rightly so. But I assured him there was a bunch of, actually I have a lot of builds in my style, so I assured him I could probably get through it. And then he said, actually, you have like 6 to 7 minutes. Now, 6 months ago, I'd have made a 6-7 joke, but my 9-year-old tells me that's no longer hip, so I'm just going to refrain from making that reference. All right, I think I've stalled long enough there in perfect timing, and I've got a controller here. Green, is that right? All right, so I'm going to try to really hammer home some of the other themes you've heard, Dan. I hope it's a good synergistic message. What I'm really going to try to do, if I can get this the right direction. Can I do it? Okay, which is the button? Green in the middle. I'm actually pushing the button. Oh, there we go. Okay. So really what I want to try to do in the interest of translating technology as what we're talking about here is to strategically focus and give advice on what I feel are some important points to strategically focus new technologies toward how they can be ultimately deployed. I'm going to highlight this again, if I can get that to work. Going once, going twice.
The big button.
Big button. Nice. Thank you very much. Maybe I can't get through 6 or 7 minutes. I'm not sure. So I do want to underscore this point because really it's roles like engineers like myself. Sometimes there's a missing link between the research at the university and then deployment at full scale. And sometimes there aren't questions that get asked in the initial stage that could really benefit you in terms of translating that to full scale. So with that, big green button, self-destruct. Okay, let's go back, go back. Technical difficulties, please hold on. Whoop, whoop. Making some progress. One more. All right, I think we're in business. Okay, so today we have 3 what the EPA has designated as best available technologies, or BATs, for drinking water. And those are GAC, granular activated carbon, ion exchange, and RO. And you can see there are a lot of advantages to using these processes. They're not called the best available technologies for nothing. We have substantial industry institutional knowledge about all these technologies. They have reasonable footprint. They accommodate large flows, those tens or hundreds of millions of gallons a day. They're relatively affordable. And I say that, I mean, no one wants to invest tens or hundreds of millions of dollars to take PFAS from 6 parts to 4 parts per trillion, but we can do it, and it's not going to really destroy the budget to do that. We can treat PFAS to non-detect, and I have that asterisk because it really depends on how you design the process, what the influent concentrations are, of course, and your analytical methods, because non-detect is not non-detect is not non-detect. These are all also compatible with potable water. They have NSF certification for contact with drinking water, so we know we can use these in a potable water application, and they're permittable. We heard talks from regulators this morning. The regulators understand these technologies. They know about them, they've seen them, and they are comfortable with you installing them as a municipal treatment application. So what else do you possibly need? We have this array of BATs. And one difference between these and potentially other technologies is these are all removal technologies. We separate the PFAS from the main treated drinking water flow. So they do that, but what they don't do is treat residuals. You still have this PFAS left over that you have to deal with. So that's one way to think about how to focus advanced technology. But wait, there's more to talk about. Let's look at the sort of the opposite side of the coin and parse some of the destructive technologies that are out there, many of in the map that Charles just showed you. So what are some of the barriers for adopting innovative, destructive technologies? And just from a list here, this is just a small sample of the things that Charles just showed. So you see the universe is big, if you will. And there are many more out there, of course. But in order to make these translate from the research arena to full-scale adoption, there are a lot of boxes that have to get checked. The kinetics, the process has to work fast enough to be feasible. It has to be adaptable. So your batch process in the lab may not translate to hundreds of millions of gallons of continuous throughput. It has to be scalable. So maybe 10 GPM in the lab is great, but 10 million gallons a day doesn't work quite so well. Footprint, obviously a very important consideration for many existing facilities that are going to have to install this in existing treatment plants. It's great if the technology does everything I want it to do, but if it requires 2 football fields to make it work, then it's not going to be very much use for me. Some of these produce potential byproducts, and that's going to go in the treated water flow, so you want to avoid that. You have to be certified. So all these new technologies that get developed, are they certified by NSF for use with contact in potable water? The regulators have to be comfortable with it. It has to be sustainable because in some utilities, that's a concern. So it needs to be energy efficient, maybe use as few chemicals as possible, and basically has to be affordable. So as you can see, there are issues with translating from the bench scale to full scale deployment. So there are some of these that are pretty difficult, but not impossible to overcome, most of the ones shown in this list. However, there are a couple that are deal breakers. So if your process is not certified for use in drinking water, it doesn't matter how efficient it is, how affordable it is, how effective it is, you still can't use it in your main treated drinking water flow through the treatment plant. And the same thing is true for your permeability. Could be great if your regulator is not familiar with it or they're not comfortable with it. The chances of getting that actually installed are pretty low. So a viable technology, a viable destructive technology has to check all of those boxes. So let's run quickly through how that might work. Barriers are high, so how can we reduce those barriers? And one way is, again, to focus on the residuals element because there's a lot of benefits to that. If you're treating just the residuals flow, then your system is going to be smaller, so your potential for scale up is better and you have reduced footprint. Obviously, small systems are more affordable, both in terms of capital and operating cost. They're more sustainable because they use less power and fewer chemicals. Usually they're faster and the kinetics are not as important for smaller systems maybe as they are for much larger tens or hundreds of millions of gallons. If your process produces byproducts, if you form, they won't matter if it's in the residuals process because they're not going to translate into the treated drinking water flow. In terms of certification for NSF or compatibility, it's not an issue if you're just focusing on treating the residuals. And for permeability, again, if you're not talking about the flow that ultimately goes to your consumer through the distribution system, maybe your regulator just doesn't care what you use in order to affect residuals management. Adaptability really depends on what the type of technology is. So maybe it works in one situation and maybe it doesn't. So we check almost all the boxes, so it tends to be, that's a good application. But there's one more thing to consider. The landscape is crowded, as Charles showed. So if you have a destructive technology out there, how can you differentiate your technology from the whole landscape of stuff that's out there and prove that it's going to be useful? I'm going to touch on that in just a second with this last slide. So a couple points. Strategically, successfully, how do we translate destructive technologies to full-scale use? One, focus on residuals. Now think two, if you were in the process of designing a treatment plant for compliance, the compliance date, as it stands now, the 2 years that EPA has proposed additional notwithstanding, is 2029. So if your process is just now getting to commercial phase, you're not really certified by NSF, the regulators don't know your treatment process that well, the chances of you getting that proven, designed, constructed, commissioned in 3 years is pretty small. So if you avoid focusing on that main treated drinking water flow, you circumvent those problems. And then finally, again, considering the crowded landscape, I would really advise you as someone who's maybe trying to get your technology moved forward, develop a value proposition that's not entirely tethered to PFAS. What else can your technology do? Can it be helpful in other ways? That will help sell your technology literally in ways that you can avoid maybe the landscape of all the other competitors that are out there. So that's it.
Thank you, Brent. That was wonderful. Not only you delivered on time, but you also staged us together so that we are ready for the Q&A.